many ways. I couldn't believe that the eclipse was like between the last cruise and this cruise. Feels like it was 8 years ago, but that's fine. Show of hands, who here got to go see the eclipse in person? Wow, so many people. Yeah, so this covered a huge swath of land that it went through major metropolis areas from Texas all the way up. Went through Columbus, Ohio, and continued on. So this was a total solar eclipse. This was also the first solar eclipse that I got to see. Yay! 2 bucket lists for me as an astronomer is like, one was going to go see a total solar eclipse, and it was super cloudy near Austin, Texas. And I've got to shout out the woman-owned Milam and Green Distillery, which invited me to be their speaker for the eclipse, which was like, could not have been better. Just put me at a whiskey distillery and have an eclipse happen, and I was very, very happy. So you could see the whiskey in my hand while I'm enjoying the eclipse. It was a little bit cloudy, but that made it kind of interesting because you basically played chicken with the eclipse because you're supposed to wear your safety glasses, right? So you don't look at the sun. It's very important. People literally do go blind every time that there's an eclipse. But when it's cloudy, that's doing what the glasses do. So you're like, ooh, I can actually see it. You can't see it with the glasses. So you're like, okay, no, oh, is it okay? Is it okay? Okay, no, okay, I'm okay. So did that for about 20 minutes and it was great. But the clouds did part so we could actually see the total eclipse and we could see the corona, and then a crow or raven flew over us and someone was like, not today, Satan, and like, it was great. It was super, super fun. If you have not gotten the chance to go see a total solar eclipse, it is as weird. You cannot overhype it. You cannot overhype it. And for me personally, I think all of you who are showing up at 9:45 a.m. on a Star Trek cruise to learn about space science, you probably have some emotional attachment to space and astronomy. And let me tell you, rolling in like a caravan of thousands and thousands and thousands of people all going to go see an eclipse from all over the world is one of the coolest communal nerdy space experiences you can have, like even beyond just the getting dark thing. So yeah, anyway, very, very cool. But there was actually some science that we do with this. So researchers do take advantage of these eclipses. There's things that we can do. So NASA funded 5 separate science projects that included chasing the eclipse with a high altitude research jet, radio telescope observations of the sunspot regions, and then radar studies of the effects of the sun's shadow on the Earth's ionosphere. So like what happens to the Earth's upper atmosphere as the eclipse is happening, because we get this sudden cool down, right? It's different from like a sunset as it's all gradual. This is like, and you're dark. and what happens to the ionosphere when that happens? And some of you, if you're into astrophotography or you were at an event where they were able to project a little bit more detail, you may have seen that feature on the bottom left. So this was a solar prominence, and there's sort of different types of solar events that happen. We have solar prominences, solar flares, and then coronal mass ejections, and they're kind of like mild to worse. But a solar prominence is basically a still tethered arc of solar plasma. So you can kind of see that red arc at the bottom, that it's still attached, but it's protruding a lot from the sun. And so that's what we call a solar prominence, and one of those was going on during the eclipse. And then you can see a little mini flare up on the top right as well. So that's when it burst forth, and it's just kind of sending a little bit of plasma out into the atmosphere. So very cool. And solar storms, as we talk about those, so this is a pretty much visual image of the sun that you can take, and you can see these sunspots on there. And sunspots happen in a fairly regular cycle. We call it the solar cycle. And it happens about every 11 years, you get these peak of sunspots. And all it is just the number of sunspots increases. But the reason for that is that the sun is not a solid ball that's rotating. You can imagine, there was like a great Calvin and Hobbes comic ages ago about it. But you can, as you're rotating and you're making one full rotation of a
solid sphere, the middle is going to have to be moving a lot faster than the areas near the top of the sphere for it all to make one complete rotation. And when it's not a complete solid, when it's made of plasma, which is ionized gas, which is what the sun is made out of, you're going to be trying to catch up with it. So it's not all just going to be one complete rotation. The entire thing is going to have some eddies and be slower than other parts. It's actually why we, have weather patterns on Earth, because our atmosphere, even though the Earth is solid, the atmosphere isn't. And so we get those jets, we get these storms that appear from the differential while the Earth is rotating. And so that's what's happening on the sun. And as the plasma is not moving all at the same rate, it kind of starts to twist up on itself. So it's charged particles. And as they start to build charge as it's rotating, you can think of it like a rubber band sort of twisting together, and it twists and twists and twists and twists, and it gets tighter and tighter. And that's where we're seeing these solar spots. So every sunspot has a pair. They're basically two ends of a magnet. And those solar prominences that we saw are the North Pole connecting with the South Pole, and all of the particles, all of the charged particles following those magnetic lines. And so that's kind of the idea of what sunspots are. And then those fields, that's what's twisting up. The North and South Poles are twisting, all the material is caught in it, and then eventually it will break. And that's when we get solar flares or coronal mass ejections. And so these sunspot cycles, again, it's usually about 11 years, and then all of the rubber bands break, and the sun settles back down, and then it keeps rotating, and they start to build back up again. And we're near a solar cycle peak right now in 2024, 2025, where we have a lot of sunspots on the sun. And that results in a lot of solar storms. So Earth has shields activated. Congratulations. We have a magnetic field because we have a molten core. So again, as the Earth is rotating, on the inside it's a molten core with an iron core. And that creates a magnetic field. That magnetic field protects us from a lot of the plasma and ionized particles that come from the sun, particularly during these big solar storms. So when we're getting a lot of solar activity and stuff is bombarding Earth constantly, this material is hitting our shield and it's being deflected around. But some of it gets caught in these different points here. Let me see, that doesn't work. I don't know if I can, let me try this. Laser pointer. Oh, look at that. All right. Woo! So, technology. So a lot of these charged particles will sort of follow this path going on either side. But then some get trapped and they don't make it around, but they get caught and then they follow and they hit these north poles or south poles, which is how we get aurora. Now, this year was particularly fantastic for aurora. Show of hands, who got to see a big aurora happen? Yeah, I didn't, so good job. I'm not bitter about that at all, and that's definitely not my second bucket list thing that I want to do, but that's fine. But these went so far south. I have friends in Scotland that they were seeing not just the green aurora lights, but it was pink and purple, and that has to do with the different layers and what in the atmosphere is being ionized. So we have nitrogen, makes up most of our atmosphere, but we also have oxygen in the atmosphere, and they're at different layers, and so it depends where the particles are hitting the atmosphere and what they're ionizing. This was a picture from Vancouver that they were able to see that. So those of you who did, you're really lucky, and you should feel really good about yourselves. But yeah, a lot of these don't necessarily cause any damage. You'll get those alerts, and like I said, you'll get those sort of NOAA blasts that say this is our prediction based on how strong the solar storms are and what we can expect to see. But for the most part, these are not dangerous, they're just nice shows, because all of the lights that we're getting, again, are the particles hitting our upper atmosphere and just ionizing the particles in there, and it makes for a nice show. There are some, because we're protected because of that magnetic field, but there are some risks. So like a coronal mass ejection, which is the really big, that's like the rubber band didn't just snap, like it snapped and it hit you in the face. That's a coronal mass ejection. And that is just coronal mass ejection. It's massive radiation particles that are then hitting our atmosphere, and those can actually do some serious damage. I've talked about them a lot. They're one of my favorite like apocalyptic space things that could happen is if a coronal mass ejection were to hit us, it would take out a lot of our infrastructure. Satellites would struggle with it. They might go down, power grids can go down. There was an event in the 1800s called the Carrington event, which doesn't sound that long ago, but like that was right at the beginning of the technical revolution, and we had transformers as we were starting to build power grids. We had telegraph lines that were being used to communicate. All the telegraph lines shocked, like they went out, and there's stories of people who were actually like using them, and they could still use them even when they were disconnected because there was so much energy pulsing through all of it. People were getting shocked. Telegraph paper was just catching on fire, and whole transformers just completely blew. Like they just blew. All these brand new ones. You can see there's like some pictures and images of it where they're all just shattered. And so just think like, that was then. If that happened now. And we've had some, like there was one in Quebec that kind of hit, and it was a little bit more targeted. And actually Quebec is one of the most hardened areas to coronal mass ejections because of that. So like their power grid is super, super secure for one of these things to happen. So anyway, big solar storms, the sun is cool, super close to us, but there's lots of cool things in space. So I'm gonna go through kind of a couple headlines. Now, part of this is you may have seen these headlines pop up. Maybe they meant something to you, maybe they didn't. Maybe you didn't see these at all. So I'm gonna go through some of the more interesting scientific discoveries that we made in space. One of the cool things was mapping out Sagittarius A star's magnetic field. So what is Sagittarius A star? That is our supermassive black hole at the center of our galaxy. So we are on Earth, which goes around our sun. That's our solar system. And then our sun is one of billions of stars in this ocean of stars, which is the Milky Way galaxy. Now you see the Milky Way at night. That's you looking down the plane of our own galaxy. It's a disc-shaped galaxy, and you're looking down it, but we're inside the Milky Way galaxy, so that's sort of our home galaxy. You can kind of think of it like the solar system is our city, and then like the galaxy is our country, you know, so it's just a bigger scale, but we're still a part of that. And at the center of the Milky Way galaxy is a supermassive black hole. Now, it doesn't really have an effect on us. It's not enough gravity. This is a common misconception, so it's okay if you thought this. The supermassive black hole at the center is not the thing that's making everything orbit around it. It is millions of stars, massive, but it affects gravitationally just the stars closest to it. What is causing us all to rotate and spin in the disk is just the more and more mass of stars as you continue going out. So we're affected by all the stars at the center from us, all the stars at the center from them, all the stars at the center of them. All of that mass builds up, and it's the same with dark matter. Dr. John Grunsfeld mentioned that yesterday. Dark matter is a big component of the mass, even in our own galaxy, that causes us to all orbit, and actually how dark matter was first found, trying to figure out how fast we were going. But long story short, so this is an image of the black hole at the center of our galaxy, which is awesome, like objectively cool. So cool, I got it tattooed. But it was 3 years ago was when this was first shown. So that was the first time you could actually see the event horizon. The collaboration that does these images is called the Event Horizon Telescope, EHT. And we have seen the black hole at the center of our galaxy before. We knew it was there because we were mapping stars as they orbit around it. So they would get close, seemingly to nothing, and then they would swing around, and then they would get close and swing back around. So we knew that there was something there. But once they were able to start imaging it, and they used telescopes from all over Earth to get different sort of data points. It was like different pixels that were spread all over the Earth to get these images, imaging over a long period of time, and they found the event horizon, which is sort of this area. So that was the 3-year ago announcement, and then I went, woohoo, and I went and got a tattoo. But what they just released this year was a mapping of the magnetic field of the energy around the black hole. So this is sort of like all of the energy stuff falling into it, all the plasma that is surrounding the black hole. And then what you can do to get the magnetic field image of that is it's basically polarized light. So some of you may have polarized sunglasses. When you have regular sunlight, that is unpolarized. So you're getting it in multiple directions. This is gonna be a little bit of a physics lesson, so I'm really, really sorry for those of you who nuked this from your brain 20 years ago. But electromagnetic radiation is electromagnetic radiation. It comes out like this. So you get one line going like this, one line going like this, and combined you have electromagnetic radiation. And they can be oriented in any configuration. But you have sort of perpendicular magnetic lines that are coming from it. And so when you use polarized sunglasses, what that's doing is cutting out half of it. So any that's coming in at an angle that's not gonna make it through your sunglasses is gonna get cut out. And you may have seen this effect if you're wearing your polarized sunglasses maybe while you're driving and you're not actively driving, but you look at some of the electrical components in your car, so maybe like your dashboard or anything like that, and if you turn your head, it goes black. And that's because the light that's being emitted from that is polarized. It's coming out in only one direction. And so as you turn your head, now your sunglasses are starting to cut out the direction that it's coming out in. And so you can do that with stuff in space. You can reorient your telescopes and see where the magnetic field lines are aligned by looking at the polarization of all of these. And so that's what they did. It's really hard to do. This is a very impressive thing. Now, what does it tell us? Because I think this is one of those things where people are like, okay, so lots of taxpayer money, whatever, went toward like figuring out the magnetic field lines. And I know I'm in a very positive audience who loves space that I don't really need to make this argument. But what's cool is the type of technology that you need to build to be able to image magnetic field lines at the black hole, at the center of our galaxy, seeing through all of the dust that's in the way, seeing through all of the other things that might interfere with that, to just image this one powerful thing that we have is pretty impressive. Now, another takeaway from it, just academically, is that the polarized light is really similar to another black hole that was imaged called M87. So with M87, it's a little bit easier because, again, when we're looking at our own black hole, it's special to us because it's ours, but just because it's close, it doesn't mean it's easier. And like I said, there's a lot of dust and a lot of stuff in the way, but M87 is outside of the plane of our galaxy, so you have a lot clearer shot at it. And they were able to image this, and M87 also looked like this, which is weird because our black hole is about 1,000 times less massive than that and about 1,000 times smaller, and the plasma that's going around it is a lot faster. So this hints that there's strong ordered magnetic fields might be more common than we thought that they were. It also hints that our black hole at the center might actually have a jet protruding out of it. So a lot of things that we image around black holes, if they're, again, you have a disk galaxy, if it's pointed at us, so perpendicular to us, we can see the jet that's spitting out of the top. It has to do with angular momentum. As stuff spins around, the angular momentum spits stuff out like this, like jets. But if we're in the plane of our own galaxy, we can't see that. But our galaxy might have a jet spitting out of it, and we can tell that because of how our magnetic field lines are organized. So cool science, objectively cool science. All right. Now we'll go on to K2-18b, a little bit of a tricky name to spit out, but one of the coolest exoplanets that we've looked at. So the JWST is looking at this K2-18b, which is an exoplanet about 8.6 times as massive as Earth, so about 8.5 times more massive than Earth. And it revealed the presence of carbon-bearing molecules, including methane and carbon dioxide. JWST also suggest and added to the suggestion that it could be a Hycean planet, which basically means that it has the potential to have a hydrogen-rich atmosphere and a water surface. Awesome. Oh, cool? Really cool. Really, really cool. So it orbits a dwarf star in the habitable zone. So we talk about the Goldilocks zone. That doesn't necessarily mean that life is guaranteed. It's the Goldilocks zone because as you go away from a star, when you're close to the star, it's too hot for liquid water to exist on the surface, and then it gets just right to have liquid water on the surface, and then it gets too cold to have liquid water on the surface. But that's not a guarantee that there is liquid water on the surface. Mars, in fact, is on the edge of the habitable zone in our solar system, but it doesn't have a magnetic field that protects its atmosphere. And so if there was water on the surface, which our rovers have shown that there likely was, because there's no atmosphere, because of no magnetic field, it's a very cat, rat, that sort of thing. But then all of that water would have boiled away and there's no atmosphere to keep that ambient temperature. So again, just because it's in the habitable zone doesn't mean that there is liquid water on the surface. But this planet is about 120 light years from Earth. It's in the constellation Leo. And it has a size kind of between Earth and Neptune, which is not something that we have in our own solar system. So it's just weird and awesome. And this is how they figured out what the atmosphere looked like. Really bizarre. So all of the white dots are the data points. And then the blue is sort of the best fit model to all of these data points. And there's errors to them, but there's definite points that jump out that you can see, particularly this carbon dioxide line that you can see there. The methane, we get a pretty good peek around where methane is. And so this is a pretty good indication that there is these molecules in the atmosphere of this exoplanet. Science is awesome. When I went to school to study astronomy, we had like 5 exoplanets that we sort of knew were there. And now we're looking at atmospheres and exoplanets. Like, it's amazing. So yeah, like I said, it lies in the habitable zone. It's known to have carbon-bearing molecules, as we see here in this data, but it doesn't necessarily mean it can support life. So again, I said it was a certain amount, 8.6 times more massive than Earth. The radius is about 2.5 times the radius of Earth, so it's a little more dense than Earth is. So the interior is likely a large mantle of high-pressure ice, like Neptune, and then it has a thinner hydrogen-rich atmosphere and an ocean surface. So they're predicted to have oceans of water, but it's also possible that it could be too hot to be habitable or be liquid. Awesome. So that's K2-18b, your new best friend. Okay. Then we had a discovery after the Gaia telescope, BH3, Gaia BH3. Doesn't sound as interesting as one may think, but it's a discovery of a black hole. And it's a discovery of a black hole by observing a star orbiting empty space. So like I said, how we kind of first figured out about our supermassive black hole at the center of our own galaxy, they were able to image this. Now, this isn't the exact image. This is an artist's rendition of what they saw. But right there where I just put the laser pointer, that is where the black hole is, and knowing the mass of this star, they can figure out how massive this thing is that's present there. And we do think like black hole binaries where one star is a black hole and the other star is continuing to orbit, so the other star has died and collapsed into a black hole. binary stars are really, 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 really common. And so this is something that is fairly easy to find. What's rare is that because the binary stars are typically born around the same time, you're not going to get one that's still just a star and another one that's a black hole. So that shows that there's a big mass difference between the two of them, that one star is continuing to just live its happy life and the other one lived hot and died young and went woohoo, and then turned into a black hole. And so that's basically what we found here, but that's what's rare. That's the rare thing. We found a lot of black holes either through the X-rays that are being emitted as stuff continues to fall into them, or from the binary of like a dead star, like a white dwarf, and a black hole that gives off X-rays. But just to see a star orbit a blank spot of space, that's what Gaia is looking for. And this is the largest black hole we found with this method. So Gaia BH1 was about 10 solar masses, 1,500 light years away. Cygnus X1, which was a really famous, that was studied a lot with X-ray flares, is 21 solar masses, so 21 times the mass of our sun. And then this Gaia BH3 is 33 solar masses away. It's about 2,000 light years away. Cygnus X1 is really interesting because I don't remember all of the details, but we studied the X-ray flares going around Cygnus X1 for a long time. And I could have this wrong, but there's a funny story attached to it, so I'm going to share it anyway. But take the science that I'm about to say with a grain of salt. So we thought Cygnus X1, I think we thought it had a white dwarf companion based on the X-ray flares that we were seeing, or it had a particular X-ray signature that was unique. Anyway, I had a colleague that was doing his PhD on Cygnus X1 and written his whole dissertation, all great, and then like a month before his defense, they reclassified Cygnus X1. And it was like, no, all of the things you thought are wrong, oh no. There was a lot of tears. But that's science. Science is really, really hard. And sometimes your favorite planet gets reclassified and you cry and then you go, well, that's how science works. And you accept it and you still hold a little special place in your heart for the planet that was or the black hole that was, and you move with the punches. So with that, Gaia BH3 is now the largest black hole we found. Now, that's not to say that in this mass range we haven't found larger black holes, but that was through gravitational wave detection, which I've talked a lot about in the past, and I'm happy if you haven't seen those, if this is your first time seeing my talks, that's what I did my PhD on, was gravitational waves. And the quick version of this is that black holes up until 10 years ago came in two sizes. One was solar mass black holes, which are these, so a few times, maybe 10, 20 times the mass of our sun, and then supermassive black holes, the ones at the center of galaxies. And scientists had evolution models where they were like, okay, over time stars will die, they become black holes, those black holes will merge with other things, and then over time they migrate to the center of a galaxy, and they've merged with so many black holes that they become supermassive. But we had what we called the intermediate mass gap. All we had was these sort of maximum at the time 21 solar mass black holes and supermassive, thousands and thousands of times the mass of a star. And then what LIGO did and gravitational waves, they detected through ripples in space-time all of those intermediate mass black holes merging. And the reason we'd never seen those before was because everything around them had already fallen in. They were like completely dark. So there was no material glowing, lighting up. It had already consumed everything around it. And so we had never seen those before, but we could detect them merging finally. And so that has started to fill in the intermediate mass gap. So Gaia BH3 is not the largest solar mass black hole that we have, but it's the largest one we've detected with this method, with finding a companion star going around it. So still really, really cool, really exciting. All right. Hot gas giants, exoplanet, WASP 43b, woohoo, this is another JWST. We were able to detect daytime and nighttime on an exoplanet. What? Okay, so what you're seeing here is this curve, this top curve, is the light that's coming from the star, its parent star, its version of our sun. And then JWST detects exoplanets by seeing the light dim slightly as planets go in front of it. It's like looking at a really bright light like this, and then a little bug flies in front of it. And technically, that light got a little bit dimmer. And because JWST is so sensitive, it was able to not just detect the day side of the star, but we also got the night side of the star. So this is another sort of version of it that you can see. So it was enhanced light here and then night side there. Weird, cool, temperature mapping, science. Awesome. I can't linger on this because I'm really running out of time. We're only halfway through, and I have a lot, and I'm not halfway through my talk. So I'm going to keep going through this. Okay, so JWST also found this star formation alignment, which was really, really interesting. So it looked at a nebula. There was not coffee in it, but it was the Serpens Nebula, which is a star-forming nebula. So we get these regions of gas, mostly hydrogen, some helium, and other stuff that's been left over from other stars dying. And this big nebula is just hot and dense, and there's a lot of stars forming out of it. So we have these protostars. That's where gas is starting to coalesce and clump together, and it's hot, but it's not so dense that fusion has started. But we're starting to see all of these protostars align. And what happened is that they were looking at all of these forming stars in this direction, and like I said, you can look sort of at the orientation and the angular momentum of what's going on in this nebula, and they found that 20 protostars, their jets, so as it's all forming, right, we have angular momentum, it's spitting out energy up and beneath it as it's starting to coalesce together. You get all this energy going up. Right-hand rule, anyone remember that? Yeah, so it spits up. They found that 20 of these protostars, their jets were all aligned within 24 degrees. So that's 360, right? 24 is actually really, really small. And all 20 of these were all aligned in the same direction, kind of showing that this star formation all is a fairly cohesive, integrated process, that the flow of gas in the nebula is starting to what's cause all of these, and they all end up fairly aligned in their rotation. So that helps think about other evolution of star systems where maybe they're fully formed, not out of the star-forming nebula, but are just out in space normally, like our solar system. You can think that maybe there's actually a lot of solar systems that are all aligned in the same direction. So that kind of helps us figure out how many exoplanets are out there. And that's because when you think of like how we were detecting exoplanets with the JWST or the Kepler telescope, you had to be looking down the plane of the solar system. If the solar system is aligned like this, you're not going to see a planet cut in front of the star. There's other ways to detect them, but it wouldn't work for what they were doing. But if we're now finding in a star-forming nebula a lot of stars all form pointing in the same direction, now that can help us narrow down how many exoplanets are out there. So just cool data science, because statistics rules. Okay. Now, to circle back to one story I shared last year, and probably a lot of you saw, one of the early findings of the JWST broke scientists. And it found a bunch of galaxies early in our universe's existence, which was not expected. So as we think about the evolution of our universe, we started out with just a quark gluon plasma, and then the quarks and gluons formed hydrogen, and when it formed hydrogen, we have what we call the recombination era, which really is the combination era because it's the first time that ever formed, and all this light is emitted, and that's sort of the cosmic microwave background that we've been able to see. And then all of that hydrogen starts to pair off and starts to grow and snowball into stars. Then those stars start to group together into galaxies while the stars are living and dying. And that's sort of our understanding of the early years of our universe. But the JWST is looking near that era, and it's like galaxy, 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 like lots of very massive galaxies that kind of broke our understanding of this evolution model. Well, it turns out, through further study, and again, this is all ongoing, so this could change, but the current understanding is that this did not break our understanding of the evolution of our universe, thankfully. That we don't have to go back to the drawing board. Maybe our universe is older than we think it is. Maybe we're paired with a mirror universe. Like all of these things that we would have to think of to try to solve this. Actually, we were able to model the galaxies that we were seeing. They're still galaxies. They're still clumps of stars, but they're not as massive as we thought that they were, because the brightness index of these galaxies that was making us think that there were a lot of stars there actually just has to do with how fast and how hot the plasma and temperature of the galaxies are. So they're just way hotter and way more energetic than our models had thought or predicted. And when you factor that in, when you say, okay, well, what if these young galaxies have a certain amount of plasma energy, a certain temperature, they're spinning in a certain direction, then it's like, okay, they should look like that, they should look like that, okay, we can sleep at night, it's fine, it's okay. So that, at least that's sort of the current model, and it's obviously still being worked on. This could change next year, but that's where things are now. All right, anyone been following that? So if you were relying on an asteroid strike in 2032. I hate to disappoint you, but you've been on an emotional roller coaster. So they announced, a few weeks ago, that there was an asteroid that had a level 3 likelihood that it would impact Earth. Now, this asteroid was, it was estimated to be about 40 to 90 meters wide, based on how bright it was. And the impacts, if that were to hit us, would be localized, right? Like the one that took out the dinosaurs was like 1,000 times greater than that. So thankfully we'd be okay. But whatever it hit would not be okay. And this was sort of the uncertainty region from a few weeks ago, which you can see Earth is like right in the middle of that. And Earth's orbit is there. But over time, we've continued observing it. And what's hard is that this is a very small object. It is to have a certain brightness, but that brightness is just dependent on what light is hitting it. It's spinning. Everything in our solar system is spinning and rotating, and orbital dynamics are really, really hard. And so those are constantly being studied. But because this is so high profile, people were like, figure it out, get better, get better, get better. And so then we narrowed it down, and everyone was like, oh no, it's like a pretty good chance that we're gonna get hit. And then they continued doing it, and as of yesterday, the likelihood of this impact is 0.000005, which is about 1 in 20,000 to hit us in 2022. So we now have effectively a 0% chance that an asteroid is gonna hit us. It's all okay. If anyone hasn't seen Carol and the End of the World, highly recommend that, because it'll give you a good thought on how humans react to news like that, which we almost saw, but we thankfully don't have to worry about now. Okay, couple more things I want to talk about before we get into the night sky viewing. LIGO, my baby, my gravitational wave detector, is continuing to operate. It went into its operation run 4 at near the end of last year. It's been up and down, but what's cool is it's now paired with CAGRA. So we have a LIGO detectors. There's 2 LIGO detectors in the US, one in Louisiana, one in Washington, and those are our L-shaped detectors. If a ripple in space-time goes by, one arm gets shorter, one arm gets longer, and that's how we detect ripples in space-time. There is a detector in Italy, that's the Virgo detector, and then there is now a detector in Japan called CAGRA. And so between the 4 of them, if at least 2 are up, ideally 3, you can make these detections. But when you have 4, not only are you making certain detections, you are able to really localize where stuff is going, and you can get a lot of good data about it. So they did make one really interesting discovery last year. They detected the collision from the ripples in spacetime of what is likely a neutron star with a compact object. And a compact object could be another neutron star, or it could be a black hole. The issue is that we found that one is a neutron star. The other one is about 2.5 times to 4.5 times the mass of our sun, which is right about where neutron stars become black holes. And we have things like the Chandrasekhar limit, which says where a neutron star will further collapse into a black hole. But this is right about on the edge of actually observing what that image is. And unfortunately, we don't necessarily have enough data on this, but it's continuing to be studied. It falls in this mass gap between the heaviest known neutron stars and the lightest black holes. And just having the gravitational wave signal doesn't necessarily tell us what that is, but we now live in a really cool era called multi-messenger astronomy, where we can combine these gravitational wave signals with traditional electromagnetic telescopes that can give us combined information to help figure out what's going on. So it's continuing to be studied. If you want to remember it, it's GW 230529, which means it was detected on May 29th of 2023, but the paper was just published last year. All right, my last, greatest, most favorite paper that was published last year was what no one has seen before: gravitational waveforms from the collapse of warp drives. An actual paper. This is not us messing around with pay-for-play research papers. This is an actual research paper that was published, and actually Sebastian Kahn was a PhD student when I was a postdoc. His name was Kahn, and that was the picture we had on his door. He's a Star Trek nerd, I'm a Star Trek nerd. We reconnected when he published this paper, because obviously 8,000 people sent it to me. And I was like, oh, Seb's on this paper. And so I emailed him, and he was like, he was like, do you remember when you printed out this is why I wore the shirt today. He was like, do you remember when you printed out the lyrics to Quark's theme song, "Come to Quark's, Quark's is fun," and put it on your office door? Because I do. That's all he remembered of me being a postdoc there. But we reconnected, we chatted, and I actually got to interview all three of these authors about this paper. It's on my YouTube channel, so if you want all the details about it. But what's cool is they were asking the question, not when we can make warp drives, but with gravitational wave detectors, which we have, that detect ripples in space-time, could our gravitational wave detectors detect the collapse of warp bubbles from other warp-capable ships? So we don't have to be warp-capable, but we can figure out if there are warp-capable species out there, if they are using Alcubierre. So cool. And so they mathed it. They mathed it using a starship approximately the size of 1 kilometer, and in the paper it says, for reference, the Enterprise E is about 687 meters long. So this is a little bit bigger than the Enterprise E. And what's key to think about here is that when they were doing the calculations, again, using the Alcubierre drive equations that we have for what warp drives would be, they had to have it, and you can kind of see up in this corner, different velocities, and they only went to 20% the speed of light. So they're not technically warping faster than the speed of light, because as soon as you go greater than c with relativistic equations, you break everything. Yeah, someone was like, yeah, that's a perfect description of what happens to the math when your number is greater than c. So they said, okay, you're warp capable, you're bending space-time around a starship, but that bubble isn't necessarily moving faster than the speed of light. But if it collapses, what would the gravitational waves look like, and could we detect them? And they detected the gravitational waves here happen about 300 kilohertz. So they're big. They actually, okay, they could be detected, but 300 kilohertz is outside of the range of our current LIGO detectors. So our current LIGO detectors are about 1 kilohertz-ish. ish, 200 hertz up to about 1,000, or maybe a little bit more than that. This is many, many times greater frequencies than that, so those ripples are just a lot faster than what our detectors, but we're building more detectors. And what's even cooler is that because the gravitational waves from these collapsed warp bubbles are so big that we could detect them in other galaxies. It wouldn't even have to be a warp collapse in our own galaxy. We could detect them in other galaxies if we had gravitational wave detectors. Now, Tim Dietrich, bless Tim Dietrich, German physicists. I've worked with a lot of German physicists, so I feel confident in saying this. He's a little skeptical. His name's on the paper. He's a little skeptical. Doesn't really believe warp drive is capable. We talk about it. We share our feelings. We share our levels of optimism. But I would say it probably goes Tim, Dietrich, and then Seb and Katie are about here, and then I'm like all the way over there in terms of positivity about it. There's a lot of things that we would have to solve technologically to have warp drive. Some things mathematically to make it work, like inverse energy or inverse mass or some exotic forms of energy that we just haven't detected yet that would get us there. But my favorite thing about warp drive, the math checks out. And for me, as a theoretical astrophysicist, that's the most important thing. So, okay. I'm wrapping up the science, but I wanted to share just a couple quick highlights because I had the great honor of speaking at the Conference for Undergraduate Women and Gender Minorities in Physics a month ago in Boulder, which is my alma mater. Yeah, really, really cool. So this is undergraduate women and gender minorities, underrepresented folks in physics that are like in their early 20s. And they had research papers and they did poster presentations. And I'm going around this poster presentation era and I'm like, there's no way I was this smart. There's no way. Like full imposter syndrome stuck in. And I was like, nope, give back my PhD. This is ridiculous. Like, I don't remember. At some point I'm sure at some point I was this smart, but these folks were brilliant. And so what I think is important to share with all of you that I wanted to bring to you that I was so inspired by is a reminder of how small day-to-day science is, right? I've just shared with you all of the big headlines from space discoveries that we found, but there is day-to-day work being done by people who are as young as 18 or 19 years old that is just moving that needle ever so further to make these big discoveries. And this is why we have to keep investing in science, and this is why we have to be excited about people who want to be scientists, because it's hard. It's really hard work. So thank you. I'm just going to go really quickly through some of these. So this was a paper on the eccentric dynamics of galactic nuclei. So Lucy Walton is an undergraduate student at CU Boulder, and she developed a model to analyze eccentric nuclear disks and how the tidal disruption of heavy stars near the galactic nebulae. So if you have heavy stars orbiting the center of a galaxy, how does that heavy star get distorted? Does it get, because it has so much more mass, could it get pulled? Could its orbit change? How does that dynamic work? So she modeled it. That was her presentation. This one, I have to read it. Marissa Bloom from CU Boulder is exploring early galactic enrichment through elemental abundance scatter in low metallicity stars. I got really excited because this is one of my favorite graphs of all time, which is the periodic table that shows the astronomical source of every single element. So does it come from exploding stars? Does it come from merging neutron stars? And so she went through all of those and she looked for high metallicity, so things like copper, zinc, yttrium, barium, all of those, trying to find how much of those metallicities are. We had a Sprite extended source far UV modeling predictions. So this was sending up a CubeSat called Sprite, which is supernova remnants proxies for reionization testbed experiment. What that means is they're looking at supernova remnants in the Large Magellanic Cloud and the Small Magellanic Cloud, which are two mini galaxies outside of our own galaxy, so little clusters of stars, to look for lines that will give us information about star formation feedback processes. So as stars explode, how does that get recycled back into making new stars? And in order to do that, that's what this satellite will be able to see, but you want to know how to process the data, and you want to know how good it's going to be. And so that's what she was doing. She was modeling how the far UV models would look on this CubeSat that is going to launch soon. And then I had comparing emission measured distribution slopes and time lags to understand coronal heating frequency. This one got me really, really excited. I shouldn't pick favorites, but this was my favorite. So this was Ava from Rice. And she is modeling ways that, so for those of you who aren't familiar, we started talking about the sun. The sun has a really weird property in that its atmosphere is much hotter than its surface. So the surface is about 5,800 Kelvin. The corona, the atmosphere above it, is over 1,000,000 degrees Kelvin. So there's this huge discrepancy. How is the surface not as hot as the atmosphere? How is the atmosphere so hot? Believe it or not, this is continuing to be a puzzle for astronomers that they're trying to figure out. And so she looked at ways trying to combine the emission measurements, so how the plasma is transferring itself, over the time lag. So comparing how the plasma moves through the corona over a period of time. So combining those two models and trying to just understand it better. Again, these are undergraduate research projects, but these are all moving that needle. So I wanted to share these with you to just get excited about what cool science people are doing every day and kids are doing. I mean, they're not kids, but young adults are doing. It's really, really impressive and really exciting. So if you're into space science, I want to point you to the Ad Astra Space newsletter. This is one of my go-tos. It's written by Swapna Krishna. She writes a fantastic, sometimes weekly, bi-weekly updates. A lot of it has to do with the space industry. So if you're curious about what's going on with NASA, with funding, with astronauts who are in space, all of that, she has fantastic layouts, nonpartisan, just here's the facts. She has access to people at NASA. She's a great, great reporter and one of my go-tos for what's going on in the space industry. And then, of course, I also frequent space.com and astronomy magazine. So, all that said, we have a few minutes left. What are we going to see tonight? What are we going to see tonight? What's up in the night sky tonight? As we talk to each other, as we try to orient ourselves, sometimes you'll be like, look at that star. And then someone goes, what star? And you have to be like, okay, so it's a little bit that way and then a little bit that way. And sometimes you'll get azimuth and altitude coordinates if you're looking, depending on what you're looking up. Maybe you have a list of things in the night sky that you want to see. Azimuth is starting at north and turning clockwise, and then the altitude is going up from there. So that's how we figure out where things are in the night sky. If you're trying to give references to people, you could say, oh, it's about 5 degrees, 10 degrees, 15 degrees. This actually works really well. This is if your arm is all the way extended out. So you can be like, oh, it's about 1 degree or 5 degrees. And it actually works really well. So this is a good way to kind of orient people and tell them where you're looking. If you don't have it, I hope some of you do. I have it. You may have downloaded it from last year. It might still be on your phone. But the Stellarium app is a free app that you can get on your phone that I like to use when I'm at sea and in airplane mode. This is a good one to use. All you have to do is just turn it on. And then it actually has a red filter mode, so it's not going to blow out your eyes. And you can, I think you just point it vertically over your head, and then it orients itself. And it picks up the GPS, and it's able to show you where things are. So it's great for finding certain objects. You can search for objects through there, and that really helps you. But here's a few things that you can look for throughout the week. Some of you may have seen there's some cool planetary alignment stuff going on. Basically, this week, you could theoretically see all 7 visible planets at once. That nothing's being obscured by the sun, which is pretty rare when you think about the combination of us going around and all the other planets going around. And so this is looking west, so this is as the sun is setting, night to night, so it's going to get harder and harder. You can see Saturn as it gets dark just on the horizon. Mercury's really hard to see, but you might be able to see it. Venus is obviously super bright, so you could check that out. Uranus and Neptune are hard to see, but they're there. Naked eye, a little bit difficult, probably unlikely, but if you have binoculars or a telescope, you might be able to see them. And then Jupiter and Mars. And there's Orion for a reference, so that's usually the easiest one to find, and that's pretty high in the night sky as we're going to be going through the week. Here's sort of another image just as a reference point to give you. So right around dusk this week, 30 minutes after sunset, you can see Saturn is right on the horizon. Thankfully, we have a flat ocean and not a barn in our way, as this shows. And the moon is waxing crescent, so it's actually, this is great for night sky viewing. I think last year we had like a full moon, so this is great. This is really good. You can see Mercury. You can see where the moon is going to be moving kind of through the course of our week. So in a couple days, the moon will be there. It'll be rising as well. So right now, I think it's just below the horizon as the sun sets, and it will continue moving up. Venus is obviously the easiest to find, and then you can kind of go down from there. But they're almost effectively in a straight line. So that's what's cool, is like if you can find Venus, you can kind of start going, and then they're bright. You know, the planets are fairly bright. They don't twinkle because they're not technically single points in our vision. And so if you find something and it's not twinkling, so it's not jumping around, if it looks solid, that's a good chance that it's a planet. So that's what we can see. That's probably the most exciting. I would just encourage everyone right after sunset. I hope you haven't gone to bed yet. You can go outside and look west and try to find the planets. This is just a quick sort of look at what we've got. To orient yourself, find Polaris, the North Star, which I have to say like Tim Curry every single time. There be Polaris. So it's easiest to find. I didn't put any labels on this because I want to be able to help you find it. But here's the Big Dipper. So if you can find the Big Dipper, this is just about, what did I have it as? This is about 8:30 at night tonight. This is what it should look like. So if you can find the Big Dipper, which is right here, here's the box, there's the handle, and then you find the North Star by going to the end of the Big Dipper and then following that line, and the first big star you hit, that's the North Star. So that's north. That'll help orient you if you don't have the app or you want to do it old school, which I also encourage. And then you keep going and you find a W here. This is Cassiopeia. And Cassiopeia, if you follow this point, you can sometimes convince yourself that you can see the Andromeda Galaxy. It's really hard to do. I've told myself I found it many times. Not sure if I ever have, because the tricky thing with the Andromeda Galaxy, so that's our sister spiral galaxy, you can't look directly at it. Like your iris can't take in that fuzzy light properly. If you look slightly off, a little fuzzy cloud will appear, and that's the galaxy. But if you're like, I found it, then it disappears again. It's really hard to find, but that's the Andromeda Galaxy. We have Sirius up here, which is cool. I'll talk about Sirius again in a second. So this is now pointing south. So you found north, and you turn around and look the other direction. Sirius and Rigel, both very bright stars, easy to find. Again, this is just after sunset. Then we have Orion. So Orion will be pretty high up in the night sky after sunset. So try to find that. That's where Rigel and Sirius, so you can kind of find those. Those are super bright. Find Orion. Orion's belt is the easiest to find. Find Betelgeuse. Find up there. Betelgeuse is a red giant, which I just think is objectively cool. We've had weird behavior from it in the last few years. It is expected to go supernova at some point, but in astronomy, at some point means within the next 100,000 years. So maybe in our lifetime, maybe not. But it is clearly red, which I think is the most fun thing. So if you can find the Orion's belt, look higher up, and you can see Betelgeuse, which is going to be bright red. And then this is where Jupiter is. So if you look just south of Jupiter, which will be really bright, you should be able to find Jupiter. Then you can find the Taurus Bull constellation, that V, which is easy to find. And the horn of Taurus is Aldebaran, which makes good whiskey. Okay. I mentioned Sirius earlier. We will not be able to see this we'll be able to see Sirius. We will not be able to see what I'm going to show you. If you had a 10-inch telescope and a super clear night this year, hopefully at some point, if you get an opportunity, if you're really into this, there's a chance you could see Sirius B, its companion white dwarf. It's the furthest away it will be. This is the years as it goes around. So in 2025, right now, it's far away from Sirius. So it's at its perihelion, I think is the right term. And you can vaguely see a little dot there, so you'll need a good telescope to be able to see it. All right, I am almost done. We're back at Aldebaran. There's Jupiter. Let me see if there's anything else. If you find Orion's belt, and you kind of go straight south. This is facing west. You go straight south and you find nothing, but in your mind, you found Vulcan. Because you can't see it with the naked eye, but that's where it is. 40 Eridani is the official name for Vulcan, so don't search for Vulcan on your app. But if you look for 40 Eri, that's where Vulcan is, which I think is just fun to find. And then Wolf 359. If you can find the Leo constellation, that's this hook looking east. Again, this is just kind of about 8:30 at night, and you go straight south, then that's where Wolf 359 is, which you also can't see with the naked eye, but it's there. All right, that's it for me. Check these things out. This is where you can find me. And thank you all very much. This is fun. Live long and prosper. Woo!